float my laser pointer over here. Okay, yeah. Hello, I'm Billy. Um, I'm going to talk to you a little bit about dynamic light scattering today. So this is a pretty typical technique that you'll see in a lot of these reviews and assessments. We'll do a little bit of basics. We'll talk a little bit about the types of instrumentation. Go through some sample considerations, which tends to be one of the biggest kind of areas of focus, and then talk a little bit about the data acquisition processing and how people, display or share the data, as well as a couple of case studies right at the end. So dynamic light scattering is the most common way you'll hear this spoke about. And so as Xiaoming said, it's dynamic because we're looking at fluctuations in laser intensity and time. Some of the older names that you'll see in literature are photon correlation spectroscopy or quasi-elastic light scattering, which is kind of one of the older. But it's typically used for measuring size range in the 1 nanometer up to a micron, maybe a little above, and we'll see why it has that size range in a little bit. But this really relies on Brownian motion as a way to first actually measure the translational diffusion coefficients of things in solution or in dispersion. And then really what's happening is you're taking that translational diffusion coefficient and doing some kind of calculation and basically doing a number of assumptions to get a size out of the system. It's used often because it's super fast and it's really pretty cheap compared to a lot of the other techniques. And it's a really easy technique to get your hands on and do. And so because of that, it's one of the most widely used techniques for nanoparticle characterization from the laboratory scale up to quality control. And so if you look at the number of submissions that have nanomaterials, you can see that a clear winner in the in the number one most used technique is dynamic light scattering, with over 60% of submissions using dynamic light scattering as part of their submission. So in this next part, I'm going to kind of want you to think through this with me. So if we look on the right-hand side here, we have this large yellow particle. So imagine that's the actual radius of a particle. And all these little, dark gray or black particles are solvent molecules. What you're actually seeing is the Brownian motion of this particle, which is the random movement caused by the collision or bombardment of that particle in solution with the surrounding solvent molecules. And so that's really the force that's being exerted on the particle that's causing it to move. So I'm going to put this out there. If you can throw a couple things in chat, what do you think influenced the speed of Brownian motion? And so this might be something that you know off the top of your head, or you can kind of piece this apart if you haven't had any experience with Brownian motion before. I'm not seeing too much so far. Here we go. Size, shape, density. Size, sure. Temperature, I like that one. Yep, size of the particle. So right. So if we go to the main factors here, the size of the particle, right, means the intervening, how much it's actually being collided with, let's say. And so in air, this is the only method for moving things, a particle in air, other than wind. But in a vacuum, The collision, the kinetic collision, is really determined by the temperature. So how fast air molecules, or in this case, liquid molecules, are impinging on a surface. The kinetic energy is dictated by the temperature. The other thing is drag. So in a solvent, the particle really isn't moving by itself. It has a solvation sphere, so it's hydrated by, you know, whatever the solvent is. In some cases, it's water. It can also be salts, other adsorbates from the system. And so it has a little slipstream around it, and it's actually dragging a certain portion of the solvent molecules around with it. And that's called friction. And so the description of the particle size relation to the viscosity of the medium, the temperature, and the drag has actually been mathematically derived through the Stokes-Einstein equation. So how this relates is the translational diffusion coefficient, so the speed at which it's translating around in a liquid, is proportional to the Boltzmann constant. The temperature, so that's the number one factor, direct proportionality to the temperature. The size of the particle, inversely proportional, and the viscosity of the medium. Of course, the viscosity of the medium is also dependent on temperature. So when you're looking at doing laser diffraction, or I mean, dynamic light scattering, excuse me, these are the three major factors you need to keep in mind. Your viscosity of your medium and the temperature of the system are impacting the diffusion coefficient. So if you want to know the particle size, you need to have rigorous control over the temperature, and you have to know the viscosity of the medium in order to back calculate to a particle size. And so I'm just going to throw a random plug for a paper that I really like here. So, and this will be in the references on the slide list, but this paper from the University College Dublin's veterinary medicine school has a really just nice description of DLS and zeta potential. And I just love the title here, is what they are and what they are not. And so this is really the fundamental thing behind DLS, is that you're measuring the translational diffusion coefficient and you're applying the Stokes-Einstein equation, which is based on the frictional drag for an equivalent hydrodynamic sphere. And so when you say you're measuring the particle size by DLS, you're actually calculating the particle size from a measured diffusion coefficient. So that's usually the number one, you know, kind of thing when you're really thinking about what is actually being measured here, is scattering intensity and diffusion coefficient, and not necessarily size. So when we talk about hydrodynamic size, there's a couple of things we need to think about. So the hydrodynamic radius is the radius of a hard sphere that diffuses through a medium. And that's really just equivalence, right? So whatever we're measuring, the translational diffusion coefficient, we're converting the size back to an equivalent sphere that diffuses in that manner. So that's what the hydrodynamic radius is. This depends, as I said before, not only just on the core size, so like the projected TEM image or the microscopy-based size, but also on the structure of the surface, the drag, the hydration, and on things like solution properties. So how does solution properties affect the things like the hydration layer or the conformation of things on the surface of a particle? And of course, we're still in assumed sphere land. And so non-spherical particles, so plates or discs, rods, rings, other weird things, they actually have different orientations under flow, and when they're not under flow, they have diffusion. They have a combination of diffusive coefficients. So both rotational diffusion coefficients and translational diffusion coefficients. And when you measure a rod, it's actually the combination of all of those things. And so the first example here, if you have, a polystyrene latex bead, it has some amount of hydrated surface. And by changing the ionic strength, you're changing the screening length, so that a bihuckle screening length, which has to do with the number of adsorbed ions on the surface, as well as how many, basically the structure of hydration of water molecules around the surface. And those are affecting that slipstream, that drag layer that the particle actually has to pull around with it. So usually the higher the ionic strength, the smaller the observed hydrodynamic radius of a particle is. Secondly, if you have something like polymer chains decorating the surface of a nanoparticle, the solvent quality can also influence the conformation of those macromolecules on the surface. So typically, if you make the solvent quality worse, so if you add an organic modifier or something that decreases the solubility of those chains, or you change again, say the ionic strength of the solution, you might get some collapse of those macromolecules on the surface, and you'll see a difference again in the observed hydrodynamic radius. And lastly, of course, the non-spherical. So these particles tend to have, a combination of, fast diffusion in their primary axis, and in the axial direction, so in the length of the rod, they'll also have a rotational moment. But in general, if you think about the length of a rod will diffuse much faster than its length if you assumed a sphere of the equivalent length. It will obviously diffuse at a level that's more akin to a much smaller equivalent sphere. So just like in the sieving example that Xiaoming brought up, you have to keep these things in mind when you're actually measuring these types of particles. So let's get into a little bit of the basic principles of dynamic light scattering. So inside a dynamic light scattering cell, so either a cuvette, depends on what you're looking at, you tend to have a laser that's interrogating a small focal point inside of the cell. You have a detector that's focused at that position so that it can see any scattered light coming back from the laser source. And what happens is, as particles diffuse in and out of this scattering volume, if they're moving in sync, coherent light, so the wave fronts from the laser can hit the particles and they will go to the detector, and there'll be some amount of phase. So just like in, when you're double bouncing somebody on a trampoline, if you bounce at the exact same time, you get constructive interference. So you get a higher intensity in this case, in the detected light, when two things are moving in phase. When two things move out of phase, you get destructive interference where the waves cancel. And so what you're really measuring in dynamic light scattering is the random Brownian motion of particles inside that scattering volume are causing constructive and destructive interference over time based on their locations and where they move through the path length. And so what you see is that the fluctuation in light intensity is correlated with the diffusion coefficients of the analytes as they diffuse through the cell. And so what this looks like is something like this, where we just have our count rate, so it's the light intensity per second. And you can see that there's some amount of fluctuation, again, from that constructive and destructive interference caused by the particles moving back and forth inside the cell. So how do we go from fluctuation in light intensity to something that we can use is by looking at a correlation function. So basically what you do is you have a reference for the light fluctuation in the intensity over time. And then what you do is you take some very infinitesimal small time step and you shift that fluctuation versus itself. And what you end up getting is a correlation where you're looking at where these two things are still in phase. So the longer that these two things are in phase, the longer, basically the slower the light fluctuation is. So the faster these two functions get out of phase, the faster the light intensity fluctuation is, and therefore the faster the Brownian motion is. And so what you see is that as you move this time step, by a couple milliseconds, you start to go out of sync. And so when two things are perfectly correlated, they have a correlation of 1. Over time, you get to where these two signals are perfectly out of phase, and that drops the correlation function off towards 0. And so the short time delay correlates to basically where there's been no movement. It's basically the original intensities. And then how fast it takes for it to drop off, that correlation is related to the diffusion and the particle size. So if we look at what kind of the raw data, so that was raw data number 1, intensity versus time. So this is a corellerogram. So it is actually the correlation function of that shifted light scattering intensity versus time diagram at all these different points. And so what we see here is kind of this typical sigmoidal decay here. And so this is the G prime, tau being the time step of the correlation. 1 being perfectly correlated, 0 being completely out of phase. And what you can see here is that you can fit this function to a number of parameters. And inside of this kind of key parameter up here in the upper right is the diffusion coefficient of the analyte. So what's actually causing the laser intensity to fluctuate over time. And again, we can use that laser intensity to go from diffusion coefficient to size. There's a couple other things in here I want to point out. Inside of the scattering vector, which is basically like an instrument function, it has the refractive index of the medium, so whatever the dispersion medium or the solution is, the wavelength of light, and the angle of the detector. And so that's usually constant for every system. And what's really important here to note is that there are no optical properties of the particles in this calculation of size. So if you look at this, there's no refractive index for the individual particles in the fundamental first principles of how DLS measures size. So you don't really need to know things like the absorption or the refractive index of the particle you're measuring from the first principles to measure size, hydrodynamic size by DLS. It's just a kind of a key thing I'd like to note. So again, here, high fluctuations in that initial raw data gives us a very short time decay because these things become out of phase very quickly. When you have a large particle, large fluctuations of light intensity with time, it takes a longer time step for these two, the initial and the phased signal to get out of phase. And so the correlation plot is shifted to the right to a later time delay. And so for this, smaller diffusion coefficient means larger particle, means slower fluctuation. So now we're gonna move to our first kind of little quiz here. So first, this kind of calls back to Xiaoming's talk. So hopefully you were paying attention. Throw some T's and F's in the chat for me for this first question. According to the Rayleigh theory of light scattering, the light scattering intensity is proportional to the radius cubed. How do we feel about that one? Okay, I'm starting to see some F's roll in. That is correct. It is proportional to the radius to the 6th power. Okay, great. I like that. The key to dynamic light scattering measurement is that it is angular dependent. What do we feel about that? Okay, I'm seeing a mix of T's and F's. So if we go back to our definition, right? Static or angular dependent light scattering is based on the intensity at different angles. So we're looking at the intensity at a single angle, but just the fluctuations over time. So now if I ask that question again, do you feel like it's angular dependent or is it time dependent? I guess is the other question. Okay, great. Yep. So basically what we're saying is that we're not measuring it at multiple angles. There may be some angular dependence depending on how big the particles are, but for DLS, you're measuring at a single angle and just looking at fluctuations over time. So it's the dynamic comes from time dependence, not angular dependence. The basic assumption of DLS is that particles are under constant movement or Brownian motion. Yeah, that one's definitely a T. To obtain the diffusion coefficient from a correlation function, one needs to know the refractive index of the particles of interest. Yep, great. So it is nice to know for later when we talk a little bit about some of the calculation stuff. But you guys had this right. False, false, true. Oh, and look, what are the most important functions for Brownian motion? Of course, I skipped forward here, but it's size, viscosity, and temperature. So those are the 3 things you need to think about, specifically viscosity and temperature when you're looking at these types of data. Great. Okay, so now we're just going to talk a touch about the instrumentation. So there tends to be 2 different types of optical setup. And so we have both of these types actually in the lab. We have a Nanoflex, the Microtrek, we have the Nanoflex and this Malvern and a couple others. But basically there's 2 modes. So there's homodyne and heterodyne detection setups. And so basically what this is the whether or not you're referencing the initial light scattering, the initial wavelength or the initial frequency of the light coming in, or if you're just measuring the scattered light as a reference. And so in the frequency or phase difference measurement, the homodyne, which is where you're just putting in light, and then you typically have a detector that's at some other angle from the incident light. So the incident light from the laser never hits it. The signal is just proportional to the scattering intensity squared. So the scattering intensity from the sample squared. Whereas in the heterodyne system, you actually have some amount of the reference or the initial intensity of the laser light that is unshifted and measured. And so in that, the signal is actually proportional to the original intensity times the scattered intensity off of your sample. And so typically what that means is that a heterodyne system has a much higher signal to noise ratio. it is a less typical way of measuring it. At least there seem to be more homodyne systems out there. But this kind of brings up two things: that when you're looking at what instrumentation is being used, things to think about are the lower limits that they can detect are dependent on things like whether or not it's homodyne and heterodyne, and whether or not the types of lasers they're using are basically what the wavelength and the power is. So if you're using a much lower wavelength of light, so let's say, like Xiaoming said, blue light scatters more intensely for small particles. So a green light might have a slightly smaller interrogation window than a red laser will, and it won't matter that much, but the laser power might. And so sometimes people will be able to measure to higher dilutions, let's say using one system, and not be able to measure as high if they're using a separate system. So if you see, you know, an example where somebody's like, oh, well, I know that in this last review I did, somebody was able to measure to this dilution. It's important to go back and double check and see if the instrumentation is the same, because a lot of times these kinds of things actually influence the range at which people can measure things. So how the system is actually set up, you tend to just put a cuvette into a little box. You have, in this case, a HENI or a helium neon laser. Usually there's at least one detector at 90 degrees. So that's so that all detected light is scattered exactly at 90 degrees. It's similar to a fluorescence detector. A lot of the new systems always come with a backscattering detector, so usually somewhere in the 170s region. And as we'll see, this is actually kind of important for measuring some things like higher concentrations, et cetera. So the backscattering angle does tolerate higher concentration samples better, which we'll see in a little bit, as well as you see some less multi-scattering, which we'll also get into here in a second. People also will use backscattering angles when they're trying to avoid dust signals a little bit more, because again, as Xiaoming said, dust particles and things like that will scatter in the forward direction more than they scatter backwards. So sometimes people use that kind of general purpose for everything. So as we'll see, it's going to be important to know how the detector is measuring and at what angle it's measuring for comparative purposes. We're looking at intensity fluctuations in time. We're turning that into a correlation and using that correlation function, a fitting of that correlation function to get our particle size and our particle size distribution out of the system. So there are a number of commercial instruments. We have at least 3 of these in our right now. So we have the Malvern Zetasizer, the Dynapro, which is a plate reader style DLS, and this heterodyne system down here, the Microtrek NanoFlex. So sample considerations. Liquid samples only for this. It's pretty straightforward because you're looking at the Brownian motion of particles in a dispersion or in a solution. You want to make sure that your diluent is as clean as humanly possible. No artifact can get in there, like let's say dust. So a lot of times people will filter their dispersant beforehand. That's often recommended. 0.22, 0.1 micron is not as good, but 0.22 microns is better. You need to know the dispersant refractive index. You want to make sure that you're controlling things like the ionic strength between measurements, or if you're doing a dilution of a concentrated sample. So knowing your ionic strength, as we mentioned before, has some influence on the hydrodynamic size. Filtering, of course, there are disposable cuvettes, but in general, for a lot of situations, you have a set of nice optical quartz cuvettes for doing measurements. And yeah, something I didn't mention is that samples that absorb and fluoresce can cause problems. So any intense fluorescence can actually be seen as excess scattering, which can further convolute your coloregram. So that's something to keep in mind. And the sample volumes can be as low as 40, 30, or 40 in the the plate reader or in the micro cuvette, and up to 2 mils. Yeah, the advantages are 0.3 nanometers up to a micron pretty easily. You can measure that. The instrumentation is very cheap, and consumables like cuvettes and syringe filters and stuff also very cheap. The analyses are super quick, can often be done in several minutes for a number of samples. It doesn't require expertise, is what they say. But a lot of people, doing DLS is more or less a black box where you put some solution in a cuvette and you hit a button with a standardized SOP and it gives you a number. And that can often lead to problems, especially when you aren't taking into account things like all those parameters we talked about: temperature, viscosity, refractive index of the solvent, concentration. And it's nice because the sample can be recovered. There are some limitations. So it tends to, the particle size, as the particle size decreases, you need more sample inside of the cuvette in order to get a proportional scattering intensity. And often the accuracy of the measurement decreases with decreasing particle size. It also doesn't work for things like cell media or samples with like a ton of sugars in them, let's say, because the media tends to scatter a lot of light and you lose some signal from your particles. Also, as we talked about before, intensity of light scattering is proportional to R to the 6. So a 1x change in particle size in the radius, if you change it by, from 1 to 2, you get about 10,000, almost a million times change in light scattering intensity, which means that contaminants like dust are really bad for the system. And of course, measuring polydispersed samples, as we'll kind of go through here in a second, is really difficult for the system. And so in this case, we just have like a 1-to-1, a 50-50 mixture of 50 and 100 nanometer particles is always skewed to the larger size just because of the inherent intensity of light for larger particles. So it always kind of looks like 90 nanometers. And of course, because we're back calculating from the diffusion coefficient, assuming an equivalent sphere, we're always assuming a spherical shape. So we don't really get any information about size. And of course, this is only yielding a hydrodynamic radius, which is not necessarily directly equivalent to other techniques like cryo-TEM. So if we think about how we analyze the particle size distributions, there's really 2 major ways in DLS. The first being a cumulants method. And so that's the typical general purpose cumulants fits in the software. And most software between companies, they'll either have like their general or general purpose fitting, or it will say cumulants. And that's this approach. And it really only works for monomodal distributions of particles. And basically what it does is it takes that corellerogram and it fits a single decay, which gives you a mean and a standard deviation for the hydrodynamic size. And it basically calculates from that single curve a single value for size and a PDI from a different inflection point on the curve. And so then often when you assume you have a multimodal system or a polydispersed system, you'll have what's either called distributions fit, multiple mode fit, or regularization. So those are all kind of lumped together. And so basically what this do is it takes that exponential curve and it's fitting a series of exponentials to it instead, in order to look at the distribution of diffusion coefficients that could describe that curve. And then it will display it as a histogram. And we'll go through a couple examples here, but so for a single mono dispersed particle population, so this is a 9 nanometer in radius, so about a 20 nanometer in diameter latex sphere. And we get this correlation function with a decay. The red line is the fit that is actually going to be used here to calculate the D. And so this fits very nicely from our equation again here. We know that all of these things are constant for the system, so we don't have to worry as much about them. But something I want to bring up is that this correlation function, often what you're doing is it's looking at a summation of these exponential fits. And so each one of these terms actually kind of means something. So inside of this B term actually is this term that contains the diffusion coefficient. And inside the C term, that second moment is what is actually used to calculate PDI. So when you think about the polydispersity index or the distribution of a typical, if somebody just gives you a Gaussian distribution, you're like, okay, the mean is the center, and one standard deviation is this wide, or you could use full width half max to calculate the standard deviation, and use that to figure out what the PDI is. In this system, it's actually calculating the PDI directly from the exponential decay. So then when you see a distribution as displayed by, say, the software, or people like to show DLS distributions, really what it's done is it's taken the mean value calculated from this decay and the PDI that's calculated based on how sloped this section is, and then it's going to generate a Gaussian based on those two numbers. So the Gaussian you actually see isn't the true value, especially when isn't a true representation, let's say. It is the mean and the PDI calculated from the decay, and then it's a representation of that. So then in the second example here, we can see a single fit. So this is again using the cumulant fit, which causes the system to force it through a single exponential, which is that red line again, which you can see doesn't quite fit this data. And this is a mixture of 1-to-1 of 9 nanometer and 50 nanometer particles. And again, you can do a number of summations of this. For this, you get a single fit will yield an RH of 20, which obviously is not representative of the sample. So if you apply regularization, you can actually divide the corellerogram into multiple decays in order to get some approximation of the actual distribution in it. And so when we look at this after regularization, you can see that we do see 2 peaks. And this again is still looking at the intensity distribution, so proportional to the D to the 6th. And so when we look at the regularized fit, we have, of course, some error, but it gives us about 7 nanometers and 43 nanometers, plus or minus 10 on the second peak. And so when you do this systematically, based on how the system is actually dividing these peaks, or dividing the the decay into different sections. In practice, DLS using the regularization can only differentiate particles that are greater than 3x different. So if you have a 20 and a 40 nanometer, it won't be able to differentiate them. This is right near the limit here where we have a 10 and a 50. So that's just outside that 3x range, and it actually does a fairly reasonable job at differentiating these two systems. And so again, if you were to use a cumulant fit or just the Z average for the system, from the single exponential decay of the system, you would get 20, which may not be representative. So now we're going to talk a little bit about some of the limitations that we mentioned earlier. And the first thing whenever you do an experiment is you have to choose sample concentrations. And so there's a lot of different versions of this. This is actually from the Malvern Handbook, and I find it very useful. The idea here is that you have these different concentration lines here in the upper right hand, and the number of particles that those represent based on a nominal assumed density of 1, let's say. And then the particle diameter again here on the bottom. And so what's important for this is that two things. One, because particle scattering is proportional to r to the 6, you can use lower range of concentrations for larger particles. And the inverse is also true for smaller. The smaller the system is, the higher the concentration might be. And that may or may not lead to problems. The lower limit for DLS really is defined by the number of particles that are inside of the scattering volume. So inside the cuvette, there's a small region where the laser is focused and the detector is also focused, and where those cross is the scattering volume. So each particle that's inside of that volume is actually what's giving the signal back to the system. And so one of the assumptions in dynamic light scattering is that there is a constant number of particles inside the scattering volume. And so for a system like this to work, in general, they say you need at least 1,000 particles within that scattering volume. And so let's say for a 500 nanometer particle here, somewhere about there, if we go up to say the line that represents, 0.001 grams per liter, we can see that we're around that 100 mark, maybe even slightly lower, somewhere between 10 and 100 particles. And so this can actually create artifacts where as the concentration of particles in the scattering volumes decreases, you get fluctuations in light that are from the concentration of particles in the system and not the actual Brownian motion of particles in the system. So in general, this kind of little pie slice of this chart here in the left is the operating region of concentrations. So you can kind of use this as a general way to think about what concentrations might be okay for the system. And so, right, so it's a balance of the count rate. You want good enough count rate. In general, we say that 1.3 to 1.5 times the scattering intensity of the solvent. So you'll get some count rates just from the solvent itself, whether it's, acetone or water. And so if you're at least 1.5 times above that, which typically is somewhere in the 100,000 counts per second to 1 million counts per second region, those are typically good counts. So if you're dramatically above that or dramatically below that, you might have some issue. And so one of those issues, especially for concentrated samples, is multiple scattering. And so multiple scattering basically just means that for each photon that is scattered off of an analyte, it might go on to interact with another analyte in the system before going out to detection. And this manifests itself in a number of ways, which is anomalous count rates and then also anomalous intensity fluctuation. And so on the right, you can see when you get to really high concentrations, you get a ton of scattering in the system. And so it's better to be in a region where each photon scattered is interacting with only one analyte. And so what this kind of looks like on the first side of the data is, this is actually the intensity. This is the residual intensity, but so as concentration of analytes increase, it tends to be proportional to the concentration. And then at some point in time, depending on what type of system you have secondary effects. So that can be particle-particle interactions like aggregation, anomalous viscosity effects, things like that. And as soon as you reach that critical concentration where you start to see multiple scattering, the relative intensity starts to go back down with respect to concentration. And so again, the minimum concentration here for a measurement should be at least 1.3 times the count rate of the solvent. And so these concentration effects then, we want to be measuring inside the dilute regime where there is no apparent change in size with respect to concentration. That's the number one takeaway. If you see, you know, somebody doing a concentration ladder of analyte and you start to see, you know, a wide change with respect to size and concentration, those probably aren't optimal conditions for a number of reasons. And so depending on the type of analyte, again, and of course, things like the, if there are viscosity modifiers in the sample, other polymeric excipients to help with stability, one of these two figures may be true, where you actually see the multiple scattering region first, where you've hit so many analyte in the system that you start to see multiple scattering before you see anomalous viscosity or particle interactions. But it can also happen beforehand. So in an example like protein aggregation, so usually you'll hit a region where you start to see aggregates before you start to see multiple scattering, just based on concentration. So those are two things to look for. You always want to be measuring in the dilute region, and you want to make sure they're working under really elevated concentrations, because for the system, elevated concentrations are bad for a number of reasons. Right, and of course, things like system viscosity being changed is also very important because it's in the calculation of size. So just another thing to keep in mind. So one of the ways that the systems actually uses to counteract concentration effects is by changing the position and the angle of the detector. So in this example here, we have basically this is a backscattering angle for both of these, but it could be true for the 90 degree. And also here, we also have a laser attenuator, which is actually changes the amount of laser power going into the system. And that's another thing that often is used. It's either automatic. A lot of people just leave the setting on automatic, which basically changes or decreases the laser power going into the system. And this is usually a function of concentration. But basically what you can do in the system is you can change the measurement position inside of the cell from being in the center. So let's say you have a very concentrated sample and you start to see multiple scattering, you can move the position, the measurement position closer to the cell wall. And that means the laser focus and the optical focus for the detector are actually seeing the scattering volume closer to the cell. which means there's less probability as opposed to being in the center for multiple scattering events to happen, because basically there's just less path length for the light getting back to the detector. And so the three major things that you'll see when people are measuring concentrated samples is either they change the laser attenuation index, so it usually goes to a lower value. They usually switch to a backscattering measurement angle, and they'll usually use a near wall measurement position. And so what this looks like in practice is something more like this. So this is slightly busy, but this is on the left hand, we have the Z average diameter. And this is measured either via the automatic, which in this case is a near wall measurement, or in the center of the cuvette. And so what's important about this is that you can see that if you measure in the center of the cuvette for a highly concentrated sample, you start to see this multi-scattering effect and a big deviation in the Z average. And also you can see it in the reported distributions here, that with concentration, you get a wide variability in particle sizes, observed particle size. Whereas in this case, they're saying the automatic is using a position near the wall. You get consistent results, which is much better. And so what's important to note that's not actually written on this slide until here is that you can fix the measurement position between measuring samples, or you can allow the system to determine the measurement position automatically. When you're trying to compare two things, if they aren't measured, or if they aren't at the exact same concentration, and you have slightly different, numbers of particles in the system, and you use an automatic setting, what you'll see in the reports is that oftentimes things like the measurement position is slightly different, the laser attenuation index is slightly different, maybe the count rates look the same possibly, but that's because they've changed those two things. And so that's an indicator. If the two things are supposed to be identical, it's better if they are measured in exactly identical conditions. And so it's just something to keep in mind when you're looking at these reports, and I'll kind of point that out here in a little bit. And yeah, so that's the takeaway for this. So now let's actually go through at least what the Malvern data acquisition setup looks like. So this is what these people are looking at on a day-to-day basis as far as like creating an SOP, et cetera. So this is actually the cuvette sample chamber here. But you can see the system is very simple. You put a cuvette in, you close the lid, and you go into the software and run it. So the first thing is sample information. And so I know I said before, refractive index of the analyte, you don't need to know it. And that's true. In order to get an intensity-based, Z average size from the translational diffusion coefficient measured by DLS, you don't need to know anything about your sample. If you want to then go and change that initial intensity distribution to something like a volume, surface, or number average, then you need to know things about your analyte, and we'll get into that in a little bit. But this is, in the SOP, that's one of the first things it asks you. Next is the dispersant, and this is one of the most critical parts of the entire SOP, in my opinion, because one, you're choosing a viscosity for the system, and the measured size is highly dependent upon the viscosity. And so because it's doing that calculation from translational diffusion to hydrodynamic size, if they're putting in the wrong temperature and viscosity, or God forbid, just the wrong dispersant, it's going to have a huge effect on the calculated size. And so in the system, there are a number of dispersants as well as a number of temperature dependent viscosity corrections if they're making measurements at different temperatures for the purpose of stability testing or whatever. But it's always important to double check what temperatures and viscosities they're using and whether or not that matches what's the expectation. Again, and also the ionic strength as far as the impact on the electric double layer and the actual amount of hydrated volume that the particle has to pull around is also important. So making sure that you're taking a look at their dispersant is very important. In this, we won't go into this, but this is a static light scattering effect that we can talk about at some point in time. But basically, you can use the dynamic light scattering at a single angle to determine the molecular weight. It is not the preferred method. This is kind of like a double back calculation method. So I think it would, if people are using dynamic light scattering for molecular weight determination, I would suggest they use a different technique. So again, and then there's the temperature setting. Obviously, they need to be controlling the temperature and reporting it. So this is another kind of important thing here. You can choose a bunch of different types of cells, and disposable ones, whatever, it's fine. But there is a correction inside the software that depends on the cuvette's material properties, because there is a refractive index for when you go through a substance. There's a refractive index change from the air to the cuvette to the liquid inside, and then back out, the light coming back out. And so this can have some effect, but it's good to know what types of cell they're using. Also, a cuvette can have some interaction with the analyte in question. So, some plastics or glasses have different interactions with different materials. So it's just something to keep in mind when you're designing or looking at a person's experiment. What cell type are they using, and are they reporting it? As far as the actual measurement part of the SOP, you can choose what detector. So are you using the back scattering detector or the 90-degree detector? The number of measurements, that's of course, we always suggest a minimum of 6 measurements, 10 runs per measurement. So this is basically taking 10 runs, averaging them per measurement, and then you do 6 measurements. And this, of course, can be set manually, but that's kind of our recommended. Now this gets to the kind of the most, I think this is the part where most of the information when you troubleshoot can be found in one of the reports. So if you're having problems with concentration or intensity, or your calorigram or your distribution is looking funky, a lot of times it comes from whether or not you're fixing the measurement position and fixing the attenuation. Again, if the amount of light the detector is seeing is too high, the system will do 2 things. It will increase it'll move the measurement angle closer to the cuvette wall, or it will decrease the attenuator index, which is a little backwards because it increases the attenuation of the laser, which means it's filtering out some portion of the intensity of the laser going into the system. So those two things are to keep the detector from getting oversaturated, because you want to have a specific, it works at a certain range where the number of photons hitting it is within a certain voltage difference. And so if you have things set on automatic and you are running a bunch of samples and you want to compare two samples and there seems to be something weird going on, oftentimes, especially when it has to do with concentration, you can always see it in, is the attenuator index different between the samples, and are the measurement positions different between the samples? And of course, you can see that in the absolute values of the attenuator index. As it starts to go down below 5, their sample is really concentrated. And of course, if it's completely, there's basically the most open, so no filter, 100% laser power on the system is attenuator index 11. That means the system is super dilute. So those are kind of the two edges. At least for the Malvern, standard cuvette is 12 millimeters. The quote unquote center position is at 5 millimeters. And so anything below 5 millimeters is going to be near wall. So you can look, usually it'll give the value of the measurement. The closer the measurement is to 0, the closer it is to the surface of the cuvette wall. Is there anything else I want to mention here? I think those are the big ones. Right, so then this kind of goes back to what I was talking about before with the 10 nanometer and 50 nanometer sample. When they're exporting their analysis mode, if they use a distribution analysis, that means they're applying the regularization. And so anything that they change inside of the analysis, the distribution analysis, won't really change the cumulant value. So the Z average and the PDI that's calculated from that initial system, it won't change depending on if they use the general purpose or the multi-narrow modes. That is dictating how many individual slices or how many decays they're using to make up that initial corellerogram. And so, yeah, so we'll actually look at an example here in a second. But so this is what a typical in-run report looks like. So you can see it has a calculated distribution based on intensity. Again, this is a representation of that 2 values that are coming from the cumulants. It has a count rate. It'll say cumulant result here, the Z average and the PDI. It'll change the PDI to width if you like. And then for the distribution, it'll apply regularization and calculate a size for you also. And the raw data, of course, during a measurement gives you the count rates, as we saw before. The correlation function, it's calculating for each individual measurement, and the intensity or whichever distribution you choose to show. So for the analyst, there's a lot of things that you can pick up from this raw data screen. And so typically, if you see any just like regular fluctuation in intensity, that's pretty much a normal signal, and it might look slightly different depending on the particle size, but it's very hard to tell from the naked eye the difference. Things like dust particles here, so where you have a very large object that randomly passes through the scattering volume and spikes the intensity, that's really indicative of dust being in the system. And of course, then there's also thermal gradients or thermal fluctuations that can cause oscillatory effects in the system. And so sometimes that'll be evident that there's something wrong with your temperature control in the system. Again, a typical corollerogram, small samples are shifted to the left. They have very fast decays, high diffusion coefficients, or small diffusion coefficients, I guess, technically. And large particles are shifted to the right. And then, of course, if you added these two things on top of each other, you could get some bimodal distribution. So this would be, say, like a nanometer thing with a micron size thing. And again, in the perfect world, this function is close to a step function for a monomodal thing. And the more sloped this function is, the more more polydisperse it is. So let's go to a quick quiz. What settings are important for DLS measurement of particle size? So this could be anything that we've talked about so far. So you can just, you know, spit a few things in the chat. Could be a physical property, could be a operational property. Yep, temperature and viscosity. I go to those first. Those are definitely some of the most important. Cuvette material, yep. Medium, yeah, or dispersant, very important. Oh, this is not scrolling. Yep, temp, concentration, yep. Definitely concentration. Yeah, so those are some of the major ones. I would say temperature, viscosity, concentration. If those are important from a sample preparation point of view, the next things being the actual instrument settings. So things like, what's your measurement position? What's the attenuator index, or how much, you know, incident light are you giving into the system? And then things like, are you using a cumulant, just single exponential to model the system, or are you applying the regularization for multiple fitting of the system? And then what diagnostic tools are there to evaluate the suitability of a method? I think I mentioned a couple of these recently. But, oh yeah, maybe I didn't mention all these. But in general, yeah, count rate is one of the number ones. So count rate together with attenuation index is, you know, a function of the concentration of the system. Repeatability, I see, that's also good. You want to make sure that you're above 100,000 counts per second. That's true. Yeah, making sure that the corollerogram, I didn't mention this, but back on the multi-scattering slide too, when you go back to that, the intercept of the corollerogram should be between usually 0.8 and 1. Above 0.6 is good. That just means that you're not out of basically out of correlation with yourself from the initial get-go, which is basically just a signal of it being too concentrated when it's well below that 0.6 value. Every once in a while, if you have something that's contaminated with micron size things, you can get a correlation function above 1. And so those are the things you want to look between, you know, 0.6 and 1. And then if the PDI for the sample as calculated, quote unquote, in the cumulant analysis is above 0.4, it's way too broad. The decay is way too shallow. And so using a cumulant will never really be acceptable for reporting the value. I mean, you can report a Z average, but I would, you know, apply a regularization to the system. And so all of that stuff that we just mentioned can be found here on kind of the post data report. And so here, you know, we have sample details, what it is, polystyrene latex 200. We have the refractive index of the material absorption, which I haven't mentioned yet. I think I have a slide here in a little bit about that. That's for when we're trying to calculate a different kind of distribution. And then dispersant, refractive index, viscosity. These are two things to always check first to make sure, you know, these are within reasonable values. Then, of course, making sure they report a temperature. What temperature is it? Sometimes, if they're using a strange solvent or a strange, you know, set of circumstances, it's important to sometimes double check the temperature that they report and the viscosity of whatever media is. That viscosity is at temperature. That might happen from time to time. The average count rates here are also reported for this sample. It's, you know, 300,000. And then here they have the measurement position and the attenuator. And so this is a good indication right here. The attenuator index is closer to 0, and the measurement position is around 1 millimeter. This is a pretty good indication that this is actually really concentrated. So even though they have good count rates, they're measuring really close to the wall and with a significant attenuation of the laser. And so, you know, it might be worth going back and doing this under a more dilute condition, even though you got good results. And then the Z average and PDI as reported from the cumulant. And then the peak here will be from the regularization. And in general, when you look at these kind of results, it'll say like result quality good. I don't really ever trust what the Malvern instrument, it's basically just saying that it was able to calculate sizes from it. So, but if somebody ever submits a report that says bad, definitely double check. So let's look at a little bit more of the data analysis. So cumulant versus distribution. So I always say, you know, cumulant is really only good for monodispersed things. It yields a Z average and a polydispersity, which are both very useful, and they're fundamentally the most basically the least amount of treatment or manipulation of the data gives you in the cumulant analysis gives you Z average and polydispersity. So those are the most accurate things that a DLS reports. And by accurate, I mean true to the system measurement principles. Let's say that instead of accurate. It usually fits only the first 80% of the function, so not that really long time step afterwards, because that doesn't actually matter as much for the size or the polydispersity. And it often represents the most small particles. And so here again, from that report before, we had the cumulant analysis part and the distribution analysis part. So the distribution analysis part is post-regularization of the system. And so this is taking multiple decays for the profile. It's going to assume multiple Gaussian distributions about the diffusion coefficients and therefore size calculated from each of those. Right, so then this last part is kind of the most important part of this, is that The size distribution reported here is the intensity initially of the regularization, is the intensity distribution. And that's totally fine. And I stand by using regularization or distribution analysis for the intensity weighted distribution. So if it says, intensity distribution, that's still looking at R to the 6. The problem really comes when people try to convert to volume or number average distributions, because that requires a significant knowledge of the particle properties. So the particle refractive index, its absorption fraction. So that's like the absorption coefficient is the imaginary part of the refractive index. And that's all put into the Me theory calculation for back calculating to volume and number. So anytime you see DLS, if it's not in intensity, any intensity distribution, it's very important that you know what the refractive index and absorption coefficient was used. And those are, because there's, basically the data is being post-processed through another set of equations, which adds additional error. So where do the D, 10, 50, and 90 come from in DLS? They don't come from anywhere. They don't really exist in DLS. It is part of the distribution fit analysis. So once it's post-regularized, and it's always weighted to either intensity, volume, or number. In general, I wouldn't classify the post-regularization fits. I wouldn't tend to use, especially like D50 in laser diffraction is volume based. So you could use the D intensity 50, but it's not typically a way that people will represent DLS data. And more often than not, using a Z average and a PDI is better. So I'm going to move on just a little bit here. So as I said before, the conversion from intensity to volume to number involves a very intense Me scattering function that has multiple parts to go from the measured intensity distribution here to the number distribution or volume distribution, and it assumes a spherical volume. It assumes a uniform refractive index for the particle, an imaginary part to the refractive index, which is the absorption coefficient. And so, whenever you're converting from the initial intensity down to the number, you need to be careful about what values you put into the system to do that. And I'm just going to show you a couple more examples here in the last couple minutes of this section. So the impact of dilution as well as the impact of the dispersant. So if you are diluting, say a primary standard, even like this, like a NIST polystyrene standard, and you dilute it into water versus diluting it into sodium chloride, just a 10 millimolar sodium chloride, not even that much, you can get up to a 10% difference in size. And this is just due to that contraction of the electric double layer on top of the particle. So identical matching of dispersant, as well as keeping this in mind when somebody does a dilution study. If the initial material is at some ionic strength or tonicity and it's being diluted down, whether or not it's appropriate to ionic strength match, tonicity match to maintain that there's no particle size change if there is an observed particle size change that's seen. And so little variations like this can easily happen just by changing the particle environment. So this is something that Xiaoming alluded to, which is the impact of dilutions on globule size distribution of and ophthalmic emulsion. And so first we can see here, there are, the same product diluted either into DI, some surfactant, the original, or sodium chloride. And there's obviously a difference in the observed particle size. And so one of the questions was, well, if we dilute this sample, how does that impact particle size? So with no dilution, again, we see it's a Z average of about 250, and then it decreases to about 98. So what is happening? Is is this dissolving? Is it actually getting smaller? So a number of things can be happening. This could be, instability. The system is falling apart. Likely that's not the reason that this happened. Particles could be agglomerating or solubilizing. But in general, this can also be an effect of those things that we saw, like being at too high a concentration and having viscosity effects. So when it's concentrated and you have some polymer in the system, your globules may be translating at a lower speed of velocity because the localized viscosity is higher. And so if you're assuming that the viscosity is close to water, you might be overestimating the size when you back calculate. And so we can kind of see this here in this, in this impact of viscosity here. So again, viscosity is on the bottom of the system here. Viscosity, of course, changes with shear rate. This is for the rheostasis sample. So we know that at low shear, undissolved sample, it is highly viscous, the rheostasis ophthalmic. And so depending on which assumed coefficient of viscosity that you use to do the calculation, you can get wildly different particle sizes. And so that's just assuming whichever viscosity depending on the dilution of the system versus water on the far right and basically a concentrated system on the left. And again, we can look at for an intensity distribution, just the general purpose mode versus multiple narrow modes using different regularizers. In general, especially if you're just looking at the intensity distribution, the Z average will never change, nor will the PDI, but you'll get slightly different D10, D50, D90 based on intensity. And so this is just another thing to note when you're looking, how are they actually doing their data processing? And so just one kind of last thing to say is that once you collect all the data and you have the intensity fluctuation in the corellogram, you can reprocess all of this data without having to redo all the runs. So you can change the material refractive index if you want to calculate a different volume or number base average. You can change the dispersant viscosity, the temperature, or the measured temperature, and the analysis mode, so that you can reprocess all the data and see how it changes if you suspect that they were using incorrect values, or if you want them to go back and reprocess it under different conditions. It's totally possible. So last quiz for the day. Accuracy of DLS is dependent on daily calibration with known size standards. Does anybody think that that's true? Let's throw some T's or F's in the chat here. I'm gonna wait until I see a couple more. So I would say the accuracy of the DLS method really has nothing to do with standards. You never have to run a standard. It all has to do with the calculation. In order to determine a size, I mean, you could compare it to a standard, but everything is based on the first principles of the fluctuation of the light and doing the back calculation. So it's always nice to have a standard run, but you don't use a calibration curve. You don't prep a bunch of standards and then, you know, compare your results to as measured standards. So you never do calibration. You can use a standard to, you know, do a reference for your system. But it's not important for actually measuring the size of other particles. DLS, the method, the 3 R's that Xiaoming mentioned before, should be evaluated using an actual sample rather than size standard. So repeatability, reproducibility, robustness. I see 1, 2 T's. Yes, true. That's definitely true. You know, you want to look through the repeatability of your reproducibility and robustness of your system for the actual, you know, type of analyte that you're studying, because a lot of times it does not apply to standards just based on the system. Dilution may impact particle or globule stability. The amount of excipient may impact dispersant viscosity, and therefore it's important to evaluate the impact of medium dilution during method development. I think this one is hopefully fairly obvious, as we've talked about how important this viscosity and concentration are during the measurement. So that one is true. Lastly, these 2 last ones, regularizer setting can impact the Z value in PDI results. That might be one of the last things I talked about. So I'm gonna have to go back. Yeah, okay, George got it, Kenny got it. Yep, okay, I'm seeing it. Yep, so when you use the regularizer setting, the Z average and the PDI are going to be the exact same. All you're going to do is change the D90, D10, D50, because it's basically just changing how the number of delays it's using to calculate across it. But the average function is always the same. Oh, and the this is a trick question. The histogram in DLS results is a real representation of the particle distributions. I would say in many ways, no, but DLS results are a real representation of the particle distribution. There's just some manipulation between whether or not you're saying, you know, an average cumulant value and you get, you know, just a Gaussian from the system versus the, you know, multiple narrow peaks mode. It is showing you a representation of the calculated particle size distribution for the sample based on the intensity. Whether or not it's a real or true representation is another question. And then these last couple, I'm just going to skip through, I think. These are more for your reference in the future, but basically any number of solutions that contains large aggregates, those are going to dominate the light scattering signal. When you have a bimodal distribution, depending on how different they are, you know, it might be very hard to resolve those. And so you might want to use a different analysis like the multiple narrow peaks fit. You can look at the attenuation factor when you're looking at the very dilute samples, but it's going to be very sensitive to any small, you know, contamination because you're letting all the laser power through. Of course, then there's other things like heterogeneous samples, which kind of goes back to the same question of the aggregates. This one's maybe one of the biggest unknown solution properties. If you don't know what the viscosity or the temperature dependence of viscosity or the refractive index of a solvent is, that's going to strongly impact the DLS results. And so you can do some things like try and, get viscosity and refractive index beforehand. So I would definitely, especially when there's a ton of stuff dissolved in there, like sugars especially, change the refractive index and the viscosity. Yep. And so the last, these things are all kind of for you guys to go through, recommendations for reviewers. So just things that we all talked about here. So what are the last things as far as, yeah, when you're looking at, somebody's applied package. So, what wavelength are they using? Do things absorb at that wavelength? What's the dispersant? What are the concentrations? What type of optical configuration are they using? What's the viscosity? Measurement position, attenuation, sample concentration. So this kind of just goes back through everything we just talked about. It's kind of a short list for you guys for your kind of recollection in the future. And lastly, there's a number of references here, basic kind of stuff up to more complicated things on theory, as well as the ISO and ASTM standards for methods for these systems. And then just some other, like a nice protocol, generalized protocol that people use. And then, the paper that I mentioned before, where it's the DLS and zeta potential, what are they and what aren't they? And with that, I think we can take a break. Sorry, I ran a couple minutes over, but let me get out of sharing.